All right, so this problem says, what is the direction of the velocity of a negative charge that experiences the magnetic force in each of these three cases? Assuming it moves perpendicular to B. Okay, so this B is coming out of the paper, there's the B, this B is going into the paper. Okay. The force on a charged particle is QV cross B. Okay. Now what I like to do is, I like to figure out the force for a positive charge. And then if the charge is negative, the force is in the opposite direction. Okay. And so you could do the following as well. Figure out the force on a positive charge. And if you want the force in the same direction, get the negative charge to move in the opposite direction. Okay. All right, so here's the force. You want a force in this direction. The magnetic field is coming out. So okay, so you can see that if you have a positive charge moving in this direction, V cross B, okay, V is in this direction, field is coming out, B cross, you want the positive charge moving in that direction. Okay. V cross B, that'll be the force on the positive charge. Okay, so that'll be the force on the positive charge. So if you have a negative charge, have it move in this direction, and the force will be in that direction. You guys understand? All right, you want the force in this direction for part B. You want the force in that direction. V cross B. So if you have V coming out, so for a positive charge, V should be coming out of the paper. V cross B will give you a force in that direction, and a negative charge needs to be moving in that direction. Yep. For this guy, into the paper. Okay, so yeah, so positive charge needs to move like that, and negative charge moving in this direction will have that force. Okay. Again, this is the best way to do it. At least I find it the best way. Velocity, magnetic field, you turn the velocity into the magnetic field. If you turn a screw like that, the direction in which the screw moves is the force. Okay. A cosmic ray proton moving towards the Earth at 5 times 10 to the 7 meters per second experiences a magnetic force of magnitude that. What is the strength of the field if there is a 45-degree angle between it and the proton's velocity? Is the value obtained in part A consistent with the known strength of the Earth's magnetic field? Okay. So the force on a charged particle is QV cross B, and the magnitude of this force is QV B sine theta, where theta is the angle between V and B. All right, so B is force over Q V sine theta. So they give you the force on this proton, 1.7 times 10 to the minus 16 newtons. Q is the charge of the proton is the same as the charge of the electron. Coulombs. Velocity is 5 into 10 to the 7 meters per second. And sine 45. Okay. So let's take care of powers of 10 first. This is 10 minus 12. That leaves it 10 minus 4 over there. So B is 1.7 into 10 minus 4 Tesla. Okay. And remember, this is a Gauss. Okay. So we are getting the right order of magnitude. The Earth's magnetic field is of the order of Gauss. Okay. And that is consistent with the Earth's magnetic field. A cosmic ray electron moves at 7.5 times 10 to the 6 meters per second, perpendicular to the Earth's magnetic field at an altitude where the field strength is 10 to the minus 5 Tesla. What is the radius of the circular path it follows? Okay. So you saw I guess we don't have the here. So you can start off with here. The centripetal force is provided by the magnetic force. Okay. Or V by R is equal to QB by M. Okay. So mass of the electron is 9.11 times 10 to the minus 31 kgs. The velocity is 7.5 into 10 to the power 6 meters per second. Charge is 1.6 times 10 to the minus 19 coulombs. And magnetic field is 10 to the minus 5 Tesla. Okay, let's take care of powers of 10. This is minus 24. That leaves minus 7 there and minus 1. So we'll make this 9.11 into 0.75 divided by 1.6. And this will come out in meters. Okay, so a circle about the width of this room. Okay, so the diameter of the circle is the width of this room. An electron in a TV CRT. What is a CRT?
Cathode ray tube?
Yep. Moves with a speed of 6 times 10 to the 7 meters per second in a direction perpendicular to the Earth's field, which has a strength of, so this is roughly on the surface, it's on a surface. What strength electric field must be applied perpendicular to the Earth's field to make the electron move in a straight line? Okay, so this is a velocity selector, and you saw that in a velocity selector you want the electric field and magnetic field to be perpendicular to each other. And the velocity is E by B, the velocity of the particle that comes off. Okay, so there's the velocity selector. Yep, there's the velocity selector. And only particles of this velocity given by that go undeflected. Okay, so we want to find the electric field strength. So the velocity is 10 to the 7 meters per second, and the field is 10 to the minus 5 Tesla. Okay, 3,000. So that's 10 to the 2, and then that's 30, so 3,000 volts per meter are the units of the electric field. If this is done between the plates separated by 1 centimeter, so if this is a parallel plate capacitor essentially, and they are separated by 1 centimeters, the voltage between them, voltage is electric field times the distance. Okay. So the voltage needed is 3,000 volt per meter times 1 centimeter is 10 to the minus 2 meters. So that's 30 volts. So you would need to apply 30 volts to this to prevent the deflection of the electron from the magnetic field. Okay, note that TVs are usually surrounded by ferromagnetic materials to shield against external magnetic fields. All right. Remember, what was a Faraday's cage?
It was a metallic conducting object
Uh,
that had zero electric field inside of it.
So this cage shielded you from external electric fields. So just like that, if you have a magnetic material, this was a conducting material, a conducting being had free electrons. This was a magnetic material whose magnets would orient easily. You could shield the external field from there. So if you are using electron beams and you don't want these guys deflected, you want to shield the Earth's magnetic field, and you use a magnetic material to. You would need to do this when we talked about those, if you wanted to detect those magnetic field created by the electrons, the currents in your brain. You would have to do it in a shielded room. You'd have to shield all the external fields. What else will produce magnetic fields? Currents produce magnetic fields and stuff like that. So, yeah, that's not a trivial thing, I guess, to do. A wire carrying a 30 amp current passes between the poles of a strong magnet that is perpendicular to its field and experiences a 2.16 Newton force on a 4 centimeter of the wire. Okay, so here's the wire carrying a current. and the field is perpendicular to it. Only 4 centimeters of the wire is in the field. What is the average field strength? Okay, so the force is I L cross B. Okay, since it's perpendicular, the magnitude of the field is that. Magnitude of the force is that. So the magnetic field strength is force divided by I times L. And L is the length of the wire that's in the field. So the force is 2.16 newtons. The current is 30 amps and 0.04 meters. So 1.8 Tesla. Okay, so that's a very strong field. I guess if a patient has a rod, metal rod, that's the kind of force you would feel inside an MRI machine, so that's why they probably don't want, but they don't want people with any metal going in there. I just recently learned that you can have metal magnetic particles in your eye. So people being in the battlefield and stuff like that, and so you can't go get an MRI machine. I mean, you can't get an MRI.
How do you even tell at that point that you have magnetic particles in your eye before you go get the MRI? Because it feels like that would be a disaster.
Yeah. Well, they know for some reason that.
Well, imagine if you got a chunk of metal in your eye from the war, you probably know.
That's true.
Yeah.
Or if you're using a grinder.
Oh yeah. Those are the people. They get So a lot of people who in machine shops and stuff like that.
And your eye will go bad really fast.
They're aware of that. I had a hair that got in my eye. I had to pull over to the side and on the drive here. What is the maximum torque on a 150 turn square loop of wire? 18 centimeters on the side that carries a 50 amp current in a 1 Tesla field. That's a strong field. That's a very large current. What is the torque when the angle is 90 degrees? Okay. Torque is mu cross B. Mu is NIA. Okay. N is the number of turns, I is the current, A is the area of the loop. And this is a square loop. Okay. So max torque is, okay, well, and so if mu is like that and B is like this, the magnitude of the torque is mu B sine theta. Okay. And max torque just corresponds to theta being 90 degrees. Okay. So max torque is mu times B. Okay, so the loop is perpendicular to the magnetic field. That's when you have the maximum torque. 150 turns. I is 50 amps. Area is 18 centimeters. Here's the conversion, Beth. The centimeter to meter conversion, your favorite.
I'm never gonna get that in my whole life. I'm always gonna mess it up. No matter how much I do.
Well, centimeter here. This is 10 to the minus 2.
Yeah.
And then you square it. All right, so the maximum torque. And what are the units for torque? Newton meter. Okay. So let's do this. $150 into so 389. And what is the torque when the angle is 8? So T is T max times sine 10.9 degrees. Okay. So for part B. So part A was that, and for a given angle, it's this maximum torque times the sine of the angle. A proton has a magnetic field due to its spin. So a proton is spinning and a moving charge produces a magnetic field. So anyway, this acts like a magnet. So if that's the direction of the spin, the proton's magnetic moment is pointing in that direction. Okay. And the strength of this thing is EH bar MC or something like that. Okay, so anyway, you guys can look it up. I forget the formula. Okay. I should remember it. So there's the formula. Okay. For the proton, that's for the electron, you just replace that by the proton mass. Okay. All right. So there's the moment. Okay, actually I should draw this arrow right on top of each other. So there's the spin. And there's the moment. The field is similar. A proton has a magnetic moment due to its spin. The field is similar to that created by a circular loop of current. So the field created by this is similar to that of a circular loop of current. Current loop, that 10 to the minus 15 meters in radius with a current of 10,000 amps. Find the maximum torque on a proton in a 2.5 Tesla field. So what would be the maximum torque on this proton in a MRI machine? Okay. So the maximum torque is mu times B. Okay. Max is that. Mu is I times A B. Okay. So max torque is I times pi r square B. I is 1.05 into 10 to the 4 amps. Pi radius is 0.65 into 10 to the minus 15 meters square. So let's take care of powers of 10. That's 10 to the 30 minus 30. So 10 to the minus 26. Okay, so that's the maximum torque on the, and when is the torque maximum? When mu is perpendicular to the magnetic field, okay? So this is sort of giving you a feel for it, but this problem is mixing up classical physics and quantum physics, so it's neither here nor there. Okay. A physicist is designing a cyclotron to accelerate protons to 1/10 the speed of light. Okay, we didn't talk about cyclotrons, but here is a picture of a cyclotron. This was the first, this is how accelerators started. Okay, you apply, this is two metal hollow Ds, that's what they're called, because they're shaped like a D. You apply an alternating current. So let's say we start a positive charge here. Okay, so you start near the center. You start a positive charge here. You make this negative, it'll accelerate toward there. And then you have a magnetic field where it'll make it go in a circle. And then when the proton comes here, you make this negative. It'll accelerate. So every time it crosses, it's getting accelerating, it's going faster and faster, and it'll go in a bigger and bigger circle, and eventually it comes out. Okay. It comes out of the magnetic field, and you have a fast moving particle. Okay, so this is called a cyclotron. I think University of Chicago is where they made it first, but don't quote me on that. So a physicist is designing a cyclotron to accelerate protons to 1/10 the speed of light. What is the speed of light?
Pretty fast.
10 to the 8 meters per second.
3 times 10 to the 8 meters per second. Good. Okay, so you want to speed it up to 3 times 10 to the 7 meters per second. The magnetic fields will have a strength of 1.5 Tesla. Determine the rotational period of the circular proton and the maximum radius of the proton's orbit. Okay, so here the radius of the orbit and v. Okay, so v is going to be 1/10 the speed of light. To make it go in a circle, you need centripetal force. You need this much centripetal force, and that's being provided by the magnetic force. Yeah. And this is the strength of the magnetic force. Yeah. So, what is it? Determine the rotational period of the circulating proton. Okay. So, T is 2 pi r divided by v. Okay, so we have v over r here. V over r is m over qb. V or qb over m. V over r is qb over m. R over b is m over qb. Yep. So there's the period. 2 pi. Proton, the mass of a proton is 1.6 times 10 to the minus 27 kgs. The charge of a proton is 1.6 times 10 to the minus 19 coulombs, and it's 1.5 Tesla. So the period, that's the time it takes for the proton to circle once, to complete one revolution. Okay, let's take our powers of 10. This is 10 minus 8 seconds. 2 pi times 1.6. This could be 1.67, but I'm not sure. We won't worry about that. Okay, 0.42, no. 42 into 10 minus 9 seconds, 42 nanoseconds. The maximum radius of the proton's orbit. So we'll use this formula to calculate the radius of the orbit. Radius will be m over mv over qb. So again, the mass of the proton is that many kgs. What is the speed of the proton? What have you sped it to?
3 times 10 to the 7.
Yep. So 1/10 the speed of light. And what was the magnetic field? 1.5 Tesla. So powers of 10, that's 10 minus 20, 10 minus 1, so 0.16 into 3, 1.6 into 1.5. So the maximum radius, that is 0.1, 0.3, so 0.3 divided by 1.5 equal to 1 over 5 meters, 0.2 meters. So this was really tabletop. 0.2 meters is The radius is about that much, so that's how big a cyclotron it was. With that thing, you sped up a proton to a tenth the speed of light. A mass spectrometer is being used to separate common oxygen 16 from much rarer oxygen 18. Taken from a sample of old glacial ice. The relative abundance of these oxygen isotopes is related to climatic temperature at the time the ice was deposited. So the idea is the following. You guys know that in Antarctica they take ice core samples. What they'll do is they'll dig a core about 3 kilometers long. 3 kilometers is from here to I-95. And what they'll do is, so ice is H2O. Okay. And this O, they'll measure the ratio of O18 to O16. Okay. This is the most common isotope. This is the other isotope. And the ratio, this is related to the global temperature. Okay. So you take the ice core and you measure the ratio of O18 to O16. And that's how they okay, so see here the global temperature. All those millions of years ago. I don't know if the ice core can give you that long a temperature range, but anyway, so that's one way of doing it. Okay, so this is a million years before. Okay. Thousands of years, so this is a million years ago for the last 1 million years. And I know the ice core sample can give you this temperature. Okay. All right. So, and how do you weigh these atoms?
Mass spectrometer, the radius difference.
Yep. So you use a mass spectrometer. And I don't know, you guys might have used a mass spectrometer in your chemistry labs. We have a mass spectrometer. Okay. The ratio of the masses of the two ions is 16 to 18. The mass of oxygen 16 is that, and they're singly charged and travel at 5 times 10 to the 6 meters per second. Okay, so what you have done is you charge these oxygen atoms singly, and then you set these fields such that only charges of velocity 5 times 10 to the 6 meters get through. Okay. So these velocity in a field of 1.2 Tesla magnetic field. what is the separation between these charges, okay? So what happens, oxygen 18 will hit, 16 will hit here, 18 will go on a bigger circle, okay? And they want you to find the difference in those two spots. Yep. What you're looking for is the brightness of the spots, okay? The brighter the spot, the more of that oxygen there is, okay? So what is the separation between the paths when they hit the target after traversing a semicircle? Okay, so this gives you M over Q is R over B naught. B naught is this field. E over B is the velocity selector. So this is M over Q is R. E over B is velocity of the particles times B, okay? So we're going to use this formula. It won't let me paste it. Okay. So, okay. So here's the velocity selector, B naught, and that's the radius of the path. Okay. So for oxygen 16, the radius is VMV over QB. The mass of oxygen 16 is, so the radius of the oxygen 16 path is 2.66 into 10 minus 26 kgs times velocity is 5 into 10 to the 6 meters per second. The charge of oxygen 16 is singly charged, 6 times 10 to the minus 19 coulombs, 1.2 Tesla magnetic field. Let's take your powers of 10. That's 10 to the minus 20, 10 to the minus 1. So this is, the radius is 2.66 into 0.5 divided by 1.6 into 1.2 meters. Point 7 meters, okay? And what will be the radius of the R18 of oxygen 18? It will be this divided by 2.66 times 18 over, it's that much heavier, okay? So just 18 over 16 times 0.7. So 0.78 meters. That's an 8 centimeter radius difference, okay? So, and so this spot will be there and that spot will be, this is 0.8 centimeter, 8 centimeter difference, 16 centimeters, that's half a feet, 6 inches difference. So you can easily separate them. Okay. But the thing is, what you want is the count difference, so the brightness spots. Yeah. And that's related to the temperature. All right.